what I can say that it's very difficult to ignore all these evils nowadays, right? So we all sort of accustomed with all these evils. And there is one evil in that sense that is very difficult to model it in a standard cosmology, which is the dark energy. And it also sort of compel us to build models which is not very usual in our standard general relativity or a particle physics. So it will be very challenging to describe this sort of a dark energy. Okay. So the idea will be in this course will be mainly theoretical. I will also give moderate sort of viewpoint from the observational point of view. I mean, why we need dark energy, how to detect dark energy, or what kind of observational challenge we have. But the main motivation will be to just give you a brief overview how to make a model for a dark energy. So I hope till now we already have some lectures on cosmology, particle means cosmic micro background, dark scale structure, everything. So we already know that two very important facts. One is that whenever we look at the sky from our galaxy, to extragalactic scale, to the cosmological scale, we know that we need more matter than what we observe. Right? And so that actually tells us that there is some sort of a dark matter which is behaves like a matter, like a non-relativistic star, but that doesn't emit energy, any light, or don't interact with the rest of the matter in our universe. So it's very hard to detect. So that is called this dark matter. Also at the cosmological scale, if you look at the dynamics of the universe, how the universe is evolving, not only the background expansion, but also how the structure, the growth of the structures are growing in the universe, then we need that there is some extra component or some extra push which is actually throwing things apart in a very rapid way, not in a decelerated manner, but in an accelerated manner. So we know that there is an expansion of the universe, but from most of the observations we know that the expansion is decelerating. But now we know that actually there is some component, some extra force over there, which actually pushing things apart, not in a decelerated manner, but in an accelerated manner. And that actually tells us that there should be something, some extra another component, which is dark energy, which is also invisible. So it is dark, but it is not matter-like, so it is not non-relativistic, but it is very highly relativistic, having a large pressure, rather negative pressure, and that is called dark energy. So the question is, when we have all this dark kind of thing, how one can detect something that is completely dark. So obviously, maybe till now you have some good understanding about that, but just to motivate this thing, that one can, even if things are dark in the universe, but one can actually detect them or one can study them. So I just want to show you a very wonderful experiment, but it's called the Nash's Grail mission. Actually, it's a PDF file. That
there's a video.
It's not a video, it is GIF.
So if you make the PDF file run from your pen drive, it will run, right?
It will run.
Most probably, because the path has to be linked in the same folder. Yeah.
Actually, satellites. One is called the Ave and another is called the Flow. And they are over the moon, and they are just emitting this light signal to the Earth. And whenever they are going to this moon, depending upon what is the structure, the mass, density, whether there is some sort of crater or there is some sort of hill or something, so there is small gravitational shift can be detected through the distance change of these two satellites, and they can actually are sensitive to up to 1 micron distance. So if you look at this, their surface gravity map, so this is the surface gravity map of the moon. Okay, this Grail has determined, and you can go closer, so you can see that depending upon the color, there will be sort of a less mass or there will be higher mass. And then when you actually look at with the actual surface of the moon, it actually matches, exactly matches. Fine. So if you just look at it and look at it, it actually exactly matches that the surface gravity with the mass density of the surface of the moon. So it actually gives us that sort of a training that even there is something that we can detect, like if you don't go to the surface of the moon and don't look at the surface of the moon in that detail, but I can do the surface gravity map, and from there I can actually infer what is the structure of the surface gravity or the mass structure of the moon. Right? So the lesson we learn from here is actually the gravity helps us, the gravitational interaction, to map all these masses, whatever there in our universe. So even if they are dark, actually we can use gravitational interaction because everything interacts gravitationally. So with that gravitational interaction, actually we can detect whether there is a dark matter or dark energy or whatever. So that is the basic lesson we learned. Okay. So now I just go to the blackboard. So there is, to start with, there will be something that I believe you already have learned. So so there, to describe this cosmology, there are two things. Act one, that we have a four-dimensional space-time. Okay, and on large scale, large cosmological scale, the universe is homogeneous and isotropic. The space part of the universe is homogeneous and isotropic. Okay. So if you have these two things, one, this universe is four-dimensional space-time with one time, three space, and the space part is homogeneous and isotropic, one can actually construct a unique metric in a comoving frame, and this metric is actually what is called the Friedman-Lemaitre-Robertson-Walker metric. Okay, so this is the metric. You have already learned it. This k parameter is actually determining the curvature parameter of the three space. It can be a flat for k equal to 0. It can be a sphere, three sphere for k equal to +1, or it can be a three hyperbola for k equal to -1. Fine. So we use this metric to describe our universe on large scale, and then we use the Einstein's equation. Okay. And the energy momentum tensor, which describes the universe or various components of the universe on large scale, and the structure of the TNE, which is compatible with this FRW spacetime, that is a spacetime which is homogeneous and isotropic in free space. The structure of the TNE is a unique structure. It should be a perfect fluid form, and this is given by this thing. So you have this energy density, and there is three pressure, three isotropic pressure, because these three space directions are equal. And that's because it is homogeneous, so all of them actually depend only on time. There is no space dependence on this large scale. When you do this inhomogeneous universe to study the growth of structure, then obviously one has to go beyond this homogeneous and isotropic space-time, and one has to consider the inhomogeneity, and both in the space and the matter, and try to see that how those inhomogeneities go. Okay, so this is the standard thing, and I am just doing it because it's a short recapitulation, because I need it. So if you do that, then the two Einstein's equation that we can get from here is basically one is comes from the 0, 0 component, and this comes from the II component of the Einstein's equation. So one can combine these two equations and one can write another equation. This equation is sometimes also called the Ray-Choudhury equation. And as I said, all these rho and C, they describe all the matter, means all the components that we have in the universe. That may be a matter, that may be a radiation, that may be something exotic. But this rho is the rho total of all those matters that is present in the universe, and C is all the pressure of all those matter, means whatever components are there. Now, one lesson one can learn from here is basically to get an acceleration, your A double dot has to be 0. But one can see that here in this equation, even if we have a curvature, that K, which appears in the Einstein's equation, but if you look at this acceleration equation, the curvature doesn't play any role. So there is no way you can have a non-trivial geometry in the free space of the universe that can drive the acceleration of the universe. So acceleration of the universe can only be driven through the whatever the matter or kind of constituent you have the universe. The curvature never can drive the acceleration of the universe. Okay. So on this thing we have another equation, because we have another quantity, because the structure, the way we constructed this Gini-Mean. So we know that this Gini-Mean also there is the identity which is called this Bianchi identity. Okay. So this is by construction, the construction that you have for Gini-Mean is Gini-Mean minus half R Gini-Mean. By construction, this Bianchi identity is not an extra equation. This is an identity that follows by construction. So the Gini-Mean follows this thing. So if you have this thing, so then we also have your energy conservation equation, which is that. Because if the total divergence of this thing vanishes, so it also vanishes. So this Gini-Mean is also divergent there. So this actually gives you the energy conservation equation. So if you take only homogeneous and isotropic part, means homogeneous and isotropic universe with this Gini-Mean kind of structure, if you use this thing, we get another equation which is basically and this equation is nothing but, if you just look at it, do this a little calculation, is nothing but the continuity equation that we have in fluid. If you have a inhomogeneous universe where this Gini-Mean is not only depends upon T but depends upon X, so these two equations, this equation actually gives you two equations. One is the continuity equation and another is the Euler equation or the momentum conservation equation. This continuity equation is basically the energy conservation equation, and you get another equation which is the momentum conservation or the Euler equation. Okay. So I hope in your structure formation you already learned this. So as I said, this equation is always satisfied, is always valid, and it is not an extra equation that we can form. This is already there inbuilt in the structure of the Einstein fluid. So we have these three equations. We have these three equations that we can use to solve. But as I said, this equation, any two of the equation is independent, because this equation can be sort of, means one can get this equation using these two equations, or I can use this and this equation to get this equation. So only three equations, only two equations are independent, right? Because this equation is nothing and not a new equation. So from here, one can see that we have three things to determine. One is this A, which is there in the H. So what is A? Another is rho, and another is P. So there are three things that one has to determine to get what is the dynamics of the universe. And we have two equations actually, because only two of these three equations are independent. So we need another equation to close the system so that we can solve the Einstein equation. Fine. Usually what we do, we actually, so we define what is called this equation of state. Which is W, which is the ratio between the pressure and the energy density of any fluid. So given this W, which relates the pressure and the energy density, so it actually flows your system. So whatever the two equations you take, together with this equation of state, you can actually you will be able to solve this system of equation and get your dynamics. So you can solve for A, and that actually gives you the dynamics of the unit. Okay. We can also define some density parameters. Which are defined as this rho. This part is sometimes also called the critical density. Okay. So the density parameter is basically the ratio of any density in whatever component you take. So let's say call it a I. So I can be moment mass. It can be a dark matter or matter. It can be radiation. It can be any exotic component, and the ratio between that thing and the critical energy density. At present, the critical energy density, if you calculate the present value of critical energy density, which is this, which is roughly 10 to the power minus 29 gram per cc, or if you write it in the energy unit, so 10 to the power minus 47 G to the power 4 in the unit, natural unit, so that you can relate all the mass or length or time, everything to the energy. So with that, one can define all the density parameters, whether it is a density parameter for the matter, okay, or the radiation, or whatever the exotic component you can have in the universe, okay, or you can define the density parameter by OK means that for curvature is given by this. So if you define all those things, so all of them actually are related with the condition that so at any point in the history of the universe, if I add the density parameter for all the components, they will add up to 1. And one can also define the present day value of all the density parameter, where we have to take this omega, rho m naught, rho c naught, all those things, and that's where you can define the present day value. Fine. Usually, I will in my class means I will describe all the present day value with the subscript 0. Okay. You know, given this thing, as I said, I have an equation of state over there, okay, and this equation of state for a matter is 0 for non-relativistic matter, whether this is a dark matter or matter, it is a highly non-relativistic. So you can ignore the pressure which actually comes from the kinetic energy of the movement of the particle, and you can ignore the kinetic energy in terms of the rest energy, and you can ignore the pressure, so that W is 0. Okay. For radiation, this is 1/3. Okay. And then you can have what is called a cosmological constant, which is W equal to minus. So if you put all these equation of state, which relates all those things, and you put over here, okay, then what you get is basically your matter scales as a to the power minus 3, your radiation scales as a to the power minus 4. You can call this is my locate. So your energy associated with the curvature scale as a to the power minus 2, and energy associated with, if you have a cosmological constant, is actually constant. So from here one can see that As the universe evolves, so your A, the scale factor actually increases. So very, very early time, obviously it's dominated by the radiation. Then at some point, matter will take care. So matter will take over. So it will enter a matter dominated. Then it will enter a curvature dominated. And even if there is a cosmological constant or some exotic component which is constant and very tiny in the early time, but at some point in the history of the universe at later time, it will always be dominated, because as we said, even if it is constant, everything will get redshifted or everything will be diluted because they have some evolution. So at some point of the time, the universe, if there is a tiny cosmological constant, ultimately the universe will always be dominated or governed by the cosmological constant. So that's the thing that one can infer from it. Okay, so if I now have all those things, okay, and I believe you also know that you can define what is called the redshift, which is basically the ratio of the size of the universe. A0 is the present value of the scale factor and A is the scale factor at any time. Usually we will put A0 equal to 1, is not otherwise stated. So these equations actually can be written in terms of all those density parameters. Right? So how these equations can be written? So I can write all these equations and I can write things as, this is a simple algebra, I believe all of you already have done it. So plus I can have any exotic component and its time dependence or its z dependence I don't know. It depends upon what kind of equation of state. Okay, for a cosmological constant I know, but if it is not a cosmological constant, if this exotic component is not a cosmological constant, depending upon what kind of equation of state will have a some z dependent property. So as I said, for a cosmological constant where omega x is -1, this gives you a fz is 1. If omega x is negative but not a constant, then omega x is constant but not -1. So if it is not equal to -1, then the fz will be okay. And well, all these things can be as I wrote you earlier. So this equation is always valid. This equation is always valid. So whatever equation of state I put over there, I can actually integrate it out and can write this functional dependence on z in terms of your one solution. And if omega x is actually a function of z, if it is evolving, it is not a constant, not -1, but it evolves, then the fz can be written so one can find it from there. So depending upon what kind of functional form you put over here, you have to integrate it to get this functional form. Okay. This integration may not be always easy. You cannot do it in analytically. You have to do it in analytically. Okay. So this is the equation that one gets from this 3h squared that equation. One can also write down the A double dot equation that I wrote earlier. Okay. So in terms of all those quantities. So this A double dot equation can be this is the A double dot equation. Now one can see that in order to get acceleration, A double dot has to be positive. There is a minus sign over here. So this whole part has to be negative. This is the positive quantity because this is the ratio of these two densities, and this is Z is positive. So this is the positive quantity. This is the positive quantity. So only thing, the negative thing, because this has to be negative, that can only arise from this term. Okay. So this actually gives you your 1 plus 3 omega x has to be 0, less than 0, in order to you get an acceleration. So as we said that to get an acceleration, whatever, so if you have the normal component in the universe, whether this is a matter or this is a radiation, I cannot accelerate the universe. The only way one can accelerate the universe, that you have to put some exotic stuff with an equation of state Wx, and that equation of state has to be negative and has some sort of this kind of bound. Fine. It has to be less than 0, but not only has to be less than 0, because the whole thing has to be less than 0, so there should be some other restriction. But one thing is for sure, is this has to be less than 0. Fine. This omega s has to be less than minus 1/3 at least, but it will be more less because there will be other term over here, so everything has to be less than 0, so that will give you some more constant on the omega, or on the W. So that one can actually do. How one can do that? Is that one can define what is called the deceleration parameter, which is Q, which is minus A double dot by A and H square. So is deceleration, because this parameter is named as deceleration, because one can see that in order to have acceleration, this Q has to be negative. Okay, so that this Q gets negative. So acceleration demands A double dot to 0 demands that Q has to be negative. So I can actually okay, so this one has to do. Okay. Now, what kind of thing I have to determine actually? So, as we said that ultimately, if I have to look at our universe and see that, okay, what kind of universe we have, what kind of constituent we have, and everything. So, there are few information that we know from some of our observables. One, the CMB, maybe already you have known that the CMB, the location of the first peak, actually from there one can infer that the universe is very, I mean the omega k is very close to 0, or the universe is, the space part of the universe is flat. The way one can infer for that is basically that when you look at the location of the first peak, so actually what you look at, so if there is oscillation on the in the CMB spectrum, so you look at some sort of wavelength, fine, and there is some sort of scale that is there in the sky, and you measure this length, this angle that this scale actually subtends at you being the observer, fine. So that's the angle that you measure, and then you see that how the angle changes depending upon how the universe, the constituent of the universe changes, fine, or the geometry changes. So if you have an angle over here, so if you have a length over here, to measure angle, okay, so depending upon, so if there is a flat, you measure an angle. If you instead of flat, you have a open universe, you measure some defined angle. Okay, if you have a sphere, you defer an defined angle. Okay, and depending upon, so if you look at the CMB, I think the CMB already you have learned. So this L that you plot, so you plot the CMB oscillation is the angular scale, which is the L, versus what is the temperature anisotropy. This L is basically nothing but 180 by theta. The theta is the angle that you measure. Okay. So depending upon whether the universe is flat, curved means open, or closed, your angle actually get bigger or smaller or equal to the flat, whatever the flat value is at. Fine. Depending upon that, your location of the first peak either shifts towards left or shifts towards right or remain at some point. Fine. So just looking at those angles, you can actually that the location means the flatness of the universe is roughly 0, or basically the universe is very very close to the flat universe. And there is a little caveat over here that I will explain later. That will I will show later. So first thing that we can infer is that this omega k is basically 0. So from now on, actually we concentrate more on the flat universe. Right? In geometry of the space car is basically flat. There is another quantity omega r naught, which is basically the amount of radiation that we have, and the amount of radiation in the universe is mostly from the CMB photon that we have. There is a small contribution from the neutrino, but otherwise the most of the amount of contribution coming from the photons that we have in the cosmic micro background radiation. And you know that this is a thermal spectrum, completely black body spectrum. You know its temperature 2.7 degree Kelvin. From there, and it is a black body spectrum, you can use the Stephen's Boltzmann law to calculate its energy, and then you can calculate what is the contribution of this omega density parameter, and this roughly comes out to be 10 to the power minus 5. Okay, so this is a very very small quantity that actually contributes to the present universe. So in that case, actually I can drop here the term, the curvature term. I can also ignore the term that is there in the radiation, because this radiation term will only be important being the fact that this is 10 to the power minus 5. So this term can only be important at the very very early time of the universe. Right? So if you just look at the present universe, where the dark energy is more important, I can actually ignore this radiation term. Fine. So what we have over here, so the thing that I have to determine is basically, so if I ignore this term and if I ignore this term, and also I know that from the condition that total things should be 1, but I ignore this and ignore this, so I know my this equal to 1. So if I know 1, I know the other. Okay. So the thing that I have to determine actually in the universe is Wx. What is the equation of state of the dark energy? Whether this is constant or whether this is evolving, and any one of these two parameters, which is as I said, these are the parameters that involve the background universe. Right? If you take the inhomogeneous universe, there will be other parameters comes into play, but for the time being, I am not considering that. I am just taking that a background universe given by the FRW geometry. The parameters are that, and then I can have some information about this. I can have some information about this, and depending upon the information, I can ignore this and this. So the thing that remains, this part and this part. This part omega m naught, omega x naught is 1, so I can determine only one, the other is determined, and this Fz actually involves this Wx, so that I have to determine, so that I can ultimately, with that I can get some information about h square, and that actually gives you the dynamics of the universe. So these are the roughly two quantities that I have to determine. If Wx is a constant, then there is a 1 and 1 component quantity. If Wx is a cosmological constant, so this is already fixed, minus 1. So I have to only determine this quantity. Okay. If W is a constant, then I have to determine this and any one of this thing. If Wx is not a constant, it's a functional dependent, then there can be some parameter that come in that functional dependence. So I have to determine then those parameters, and then one has to see that depending upon the present accuracy of the data, how many parameters can be determined in the Wx. So not I can write a Wx a functional form of any kind of function, and there will be some sort of thing that if this functional form contains 10 parameters, it may not be possible for me to determine all those 10 parameters. So there is a restriction of the number of parameters depending upon your observational accuracy. Okay. So given the fact now that I can ignore omega k equal to 0, so I can write now my Q, okay, I can write now my Q, and if you just do it, a simple algebra, because I already have this A double dot expression, so that I have over here, H square expression is given by this, I put everything, and then the thing that I got, I can get is basically, and I also use that this and this is actually 1, what I get is the expression that I will get. This is a very simple expression, so that's the expression I get. Okay. So and as I said that to get an acceleration, my q has to be negative. So this has to be less than 0, and this actually gives you the constant that your WD is less than minus 1 by. So that is the constant. As I said initially, the WD was 1 plus T, Wx was negative, but that actually one has to take the all other term, and that actually you can get this kind of thing. So if you have around 0.7 over here, which is the dark energy contribution in our universe, so this comes out to be minus 0.6263 or something. So that actually the constant that we have. So I have to actually now build up a model to extend the dark energy with the equation of state, whether it's a constant, whether it's a cosmological constant, or whether this is evolving, but ultimately its equation of state has to be less than minus 1/3 omega d. So whatever the omega d we have, so that has to be there. Okay. So now, okay, so this part is there. So now I just, with this background, I have to just say a few things that how we are sure that there is a dark energy. So this is the theoretical part that okay, I can have to put okay, if there is acceleration, we have to do also to include all these exotic components within this kind of characteristics. But let's see that what are the observational, basic observational facts that actually compels us to see that okay, the universe may be currently actually accelerating. Right? So let's do that. Okay, so first, one of the first sort of hint that the universe may be accelerating or there is some sort of component like cosmological constant is there is actually gained by calculating the age of the universe. So this was some before supernova people were a little bit sort of doubtful that whether a decelerating universe is actually compatible with the oldest objects that we can see in our universe. There are some oldest objects like globular cluster that are there in our universe, and one can determine the age, and then one can find that there is some sort of discrepancy if you consider a universe which doesn't have a cosmological constant. It cannot produce the right amount of age that is necessary to explain those oldest objects. So let's see how. Okay. So already we know that this thing we know. Let's say A0 I just take 1. So that actually gives you, so if I just take a derivative of this, so this gives you dt is minus z. Okay, so that is a simple calculation. And from here one can actually calculate the age of the universe, which is up to the present time. Okay, just write Ez and then I just explain what is Ez. Ez is, if you remember, I wrote h square is h0 square plus some quantity which depends upon z dependent, where which is omega m0, 1 plus z cu, omega unknown, and all those things. So I just write Ez is this h by h0. So this quantity square root I call it Ez. Fine. So whatever the quantity we have inside that thing, we have the z dependent. Square root of that I call it the h by h. So this no, there will be minus sign over here, so that minus sign will take care of it. Okay, fine. So So, so if you remember, my Ez was roughly, there is some, let's write it again. Let's say I talk a cosmological constant, right? So this is this, and then you have yes, I have a cosmological constant. If I put over this equation over here, and omega r naught, as I said, this is around 10 to the power minus 5. So it is very easy to convince yourself that in the edge, the term that actually contribute is from the terms which actually dominates in the low redshift. With the high redshift, obviously the inverse, the age was fraction of a second or some second. With an age with a billion years, that actually doesn't contribute. So the main contribution actually comes from the terms which are actually dominate in the low redshift. Right? So I can actually ignore the omega r naught term, because that omega r naught term 1 plus z2 doesn't contribute to the inverse, because that term will only be dominant in the very early time when the inverse is some a second or some fraction of a second old. That actually doesn't contribute to the total age of the inverse of B inverse. Right? So I can safely drop that one, I don't lose any sort of information. So if I do that, so what I get, my P0, if I just put over here and do the calculation, my P0 is so let's calculate this for a flat universe, which is omega k naught. Okay. Let's calculate it for a flat universe, because as I said that all the observations, the CMB actually predicts us that we have a flat universe. So let's calculate a flat universe, and let's assume that there is no dark energy. Okay. So there is no dark energy, no cosmological constant. Universe is only governed by the matter at the left side. So then this equation, just some mistake, this x will be here. So then this can be easily integrated. One can easily integrate it. If I drop this thing, this can be easily integrated. And then one can get your T0 is roughly 2 psi 1 upon h. Means one can do this integration. It's not very easy. So if you have a only matter dominated universe, the radiation you can ignore. There is no dark energy, no curvature, there is a flat universe. Your age is given by just actually 2/3 1 upon h. Now this h naught, which is actually written as this, and there is a bound on age which is roughly 0.72 plus minus 0.08. And this is from W map or Planck actually gives roughly that, a little bit smaller than that. So if you put that thing over there, okay, if you put that thing over there, then the age that this comes is actually 8.2 giga-year. Now, if you look at this, as I said, that they are oldest objects in the universe, like globular cluster, different object, and if you look at them, it's consistently the observation actually suggests that this age in the oldest object that we have, if they have a age greater than 11 giga-year or something. So means you should have, there are objects which have the age which is more than 11 giga-year. So one can see that just if you have a only matter dominated universe, this actually cannot explain the age of this some oldest object that is there, because this age that you calculate is between this, which actually cannot explain this kind of object. So that is the first problem that that people was puzzled that what is happening actually. Okay. So let's do it. The same thing. Let's do the same thing for a universe which has a dark energy, let's say cosmological constant, but no curvature. Okay. If you do that, so I just ignore omega k. Omega k I put equal to 0, but I keep omega dark energy, and given the fact that omega m naught plus omega dark energy naught is 1 as a flatness condition, then what actually you get is h E naught is given by, this is an integration, you can do the Mathematica or whatever, or you can use by hand also using your skill. So this is the integration that you can do. You can put in the Mathematica or you can do this. So let's plot this. Fine. So I just take this side. So your H naught E naught is given by this. Okay. Now one can see from here that if omega m naught okay. So let's plot it first. Now one can see from here if omega m naught is 0, then one sees that this is 1 minus 1, so the age actually goes to infinity. Right? So that's the first thing you can get. So if I have a dark energy dominated universe, so just pushing up the amount of dark energy, I can actually pushing up the age of the universe. Right? So that I can do. So let's plot it. Then what you get, the plot is I just plot H naught E naught over here and omega A naught over here. So around 1, so there is a band which actually gives you the H constant which comes from the W map or whatever. There is some bound that I wrote for the age of the universe. For W naught means H naught you can have, from there you can calculate the H naught. So this is the bound that W map gives, which is P naught is 13.73 plus minus 0.13, the bound that you get. Now if I plot this thing, it will just come out like this. It will approach to that value E naught equal to 2/3 1 by H naught, which is for omega n equal to 1. So if I have omega equal to 1 over here, so this actually goes to that value, that 2/3 H naught kind of value. Right? Because as I showed earlier, if for a only matter case, this goes to the P naught equal to 2/3 1 upon H. This is a kind of bound that I can get, that I said that is the kind of bound which is around 0.8, which comes out to be the globular cluster age. So the minimum age that we require to explain the age of the globular cluster. And one can see that you can satisfy this kind of thing once you have, this is roughly around 0.4. Okay, so if we have omega m naught which is less than 0.4, you can actually satisfy this globular cluster age, so that you can go to this kind of range which actually satisfy the omega m W map bound, or the bound that the minimum at the age of the universe should be that kind of a globular cluster, that kind of constant that you can have. Okay. So this actually gives you a first sort of hint that the age of the, means from the calculating the age of the universe, that we need maybe something which actually has some sort of dark energy or some sort of cosmological constant. These I have calculated through a cosmological constant, but one can do it for other dark energy models. But The graph is roughly the same, the numbers can vary a little. Okay. So this is the first clue that we need some exotic component or some cosmological constant kind of behavior to explain the dark energy. So let's now go to the other thing, means the other constant that comes. So this is now roughly the cosmic archaeology through which we actually sort of study our universe. So the first one, as you have already studied, is the CNV, okay, which actually probes if there is some quantum fluctuation in the very early universe, so it just probes directly to this quantum fluctuation. Not only that, it just has this quantum fluctuation evolves through different cosmological history, and that actually imprints whatever the evolution of the universe we have, including the sort of constant coming from the dark energy. Then you also have studied the growth of structure formation, okay, because to grow the structure, the universe, that actually comes due to the fact that the gravity is attractive, so things actually collapse and form the structure. But at any point, if the universe is accelerating, so that actually will show that actually gives you some sort of repulsive effect. So any kind of repulsion or any kind of dark energy component and actually slows down the growth of structure. So studies the growth of structure actually can be also constant the dark energy. And then supernova is the direct probe, okay, of the dark energy, because here we actually directly measure the distance, and knowing the distance, because any distance can get changed whether the universe's expansion is decelerating or the universe expansion is accelerating. So looking at those distances, one can actually probe the dark energy component. So let's talk about supernova first. So what are these? So things that we need is basically what is called the standard candle. So as we know that if we have any bulb, light bulb over here, and we put the light bulb at different distances, if I know what is the actual luminosity of this bulb, which is 10 watt, 100 watt, or 200 watt, then putting at different distance, then I measure the flux that I receive from there, which actually falls as a 1 upon square of the distance. Right? So knowing then the measuring now this apparent flux and knowing the actual wattage of the bulb, I can actually calculate the distance, and that is what is exactly done for the supernova. Right? Only thing is that the supernova, so that's the way. So the supernova type 1 can be considered as a standard candle, because it seems that we may know the actual luminosity of the supernova due to some reason that I will explain later. Just now, okay. But just to see that these light bulbs are huge light bulbs. So a standard supernova type 1, the weightage, means if you just see the amount of flux that it emits, is around 10 to the 48 watts. If you just convert that energy to watt, compared to sun, it's actually 10 to the 26 watts. So you can see that it's a huge one. I don't know. Okay, so what is this type 1 supernova? So these are actually, there is a white dwarf binary. So there is a binary, so there is a white dwarf star, which is a very compact object. It's a very highly gravitating, and then it has a binary. So due to its huge gravitational pull, it actually attracts matter from this binary, and as it attracts matter, its mass gets increased, and at some point of the time, it reaches this Chandrasekhar mass limit, which is the 1.44 solar mass. So at that point of time, its electron degeneracy pressure cannot actually resist its gravitational collapse, so the thing starts collapsing, and it starts collapsing, so it's actually become very hot, and it actually then triggers this thermonuclear explosion. Right? So there is some sort of thermonuclear explosion, and then you see this supernova type, this supernova explosion over here. The thing is that from here one can just see that all these explosions happen exactly roughly of the order of 1.44 solar mass. So the amount of energy that it emits is basically roughly the same, because all these explosions happen around 1.44 solar mass. So that's why one can say that this supernova type 1 that we used to see in the sky, they are roughly of the same absolute luminosity, which is related to this 1.44 solar mass. Now these are these objects that was first proposed by Dickey and Maddox in 1930s, and then, as I said, they are extremely bright. The wattage is very high, and how one can classify this supernova? Actually, it's classified through means whether the absence or presence of certain spectra in the structure. So if there is no hydrogen or there is a hydrogen, we classify these as a supernova type 1 or type 2. Now if there is no hydrogen, if there is a silicon line, we call it a type 1A supernova. If there is no silicon line, then we can further categorize it. Usually, so that type 1A supernova is there is no hydrogen and there is a silicon line, and these are thermonuclear. So how we do this thing to study the cosmology? So as I said, we have a homogeneous and isotropic effort W metric. Okay. So this is a metric that we know. And as I said, so there is a source over here which is emitting light isotropically in all directions. Okay. And you have an observer over here. Let's say the distance is what is called dl. I will explain what is distance. Let's say this is the distance d. Okay. And then if you know this absolute luminosity of the supernova, so there is the amount of flux that we receive, the apparent luminosity you can call, will be this absolute luminosity. By all the lights isotropically distributed in this sphere, which is the surface area of 4 pi ds square, so the d is the distance. So this is the apparent luminosity you can receive, the flux per or the luminosity of the photon emitted per unit area. Right? Only thing is that this distance is something different. First of all, I have to calculate this distance in a homogeneous and isotropic, okay, and a light propagation. Fine. So light propagation ds square will be 0. So I have to then take this equal to 0 and then I have to calculate the distance over. And that distance will actually comes out to be just this part. Okay. Now there is another extra part which is 1 plus z when comes over here, that is 1 plus z square. So there is a 2 1 plus z square parts coming. That is due to the fact that these photons are emitted and you look at the energy of the photon per unit area, so the total flux, fine. But as the universe is expanding, this photon energy is also redshifted. So there is 1 plus z factor comes due to the redshift of the photon energy. And another 1 plus z comes because then you can calculate this luminosity as the per unit time. So the time actually also gets dilated due to the expansion of the universe. So there is another 1 plus z factor. So total together you have a 2 1 plus z factor. So it comes out to 1 plus z whole square and the distance square that we measure in a FW space. Okay. So I can define all the kinematical quantity. As I said, initially there is one kinematical quantity which is the velocity, which is the Hubble parameter related to the A dot. I also define another kinematical quantity which is the acceleration, Q parameter, which is related to the A double dot. And then you can carry on constructing all other kinematical parameters depending upon A triple dot, A triple means 4 dot and all those things. So these are all kinematical quantity can be calculated from distance. Distance, then velocity, then acceleration, then the triple dot is sometimes called the jar and so on and so forth. So you can use all those kinematical quantity. You can go to the Weinberg book. I am not going into detailed calculation. It's an easy calculation, some algebra, some Taylor expansion you have to do. But ultimately one can write these expressions as this kind of thing. So this is, one can see that if I do first term, it depends upon z, then z square, then z cube and so on. So if I just concentrate on the lower redshift, very close to our observer means our Earth, then I can only concentrate on z. So then in that case, H0dl is just z, fine, just linearly integrated with the z, and that is basically the Hubble's law. But as I go to the higher redshift, I have to take then this Q0, then the jar, and all those things. Fine. So now looking at this dl, if I measure, I know this L, I measure this small l, then I can measure this dl. And if I measure this dl at different redshift, maybe the higher redshift, because if I can observe supernova at higher redshift, I can start actually measuring Q0, Z0, and so on and so forth. So that is the basic observational way to use supernova to do this. So these are these parameters. So in practice, what we measure is basically what is called this distance modulus. Okay. So this is this thing. So what is this thing actually? Let's just explain a little bit. How? Time is over. Oh. Okay. Okay, I just finished it and then I will. Oh, Supratik told me it's 1.5 hours. Sorry, I have no clue. Okay, so usually what we do in this kind of observation, what we measure, what is called is magnitude. Okay, so what is this magnitude? Let's say I have two objects, whatever, supernova or whatever, and their apparent flux that we receive, fine, which is, let's say, one is F1 and another is F2, fine. So this flux is basically nothing but you have this absolute luminosity and then whatever you receive, 4 pi is dm square. So let's say I have these two flux that I receive from these two objects. Depending upon the flux received, the object will be, somebody will be more brighter, some will be more dim, fine. So the magnitude is basically created light. So if so this is m1 minus m2 is minus okay. So it says that if I in my some criteria I have one magnitude is 1, another magnitude is 5, or another magnitude is 6, then if I put over here, one can see that F1 is 100 times brighter than F. So this is the way one actually have this idea. So this mu is nothing but, so for any supernova I have a absolute magnitude. No, so just to compare, I can say that for my sun, this M1, so one can see that the more the magnitude is, it's less bright, so it is dimmer, fine. Smaller the magnitude is more bright, fine. So for sun is roughly minus 2.7 for sun, and let's say for moon, it is roughly minus 12.6. So this mu, what you call is distant modulus. So if I have any object and I know its absolute magnitude, and then I observe it and I know its apparent magnitude, which is, let's say, m. Okay. So this mu is nothing but m minus m, and this is given by. Okay. So that's the thing that I measure. So I just finish this supernova thing. So just to see that there is some correction factor 25 comes, so that is not an important. But let's say that I have one supernova which is measured at z is equal to 0.026, which is n is 16.08. There is another supernova which measures at z is equal to 0.26, is n is 24.32. Let's say. Now if I take this supernova, as I told earlier that if you get to very low redshift, so I can only take this first order term, I can drop out the higher order term because the z is very small. So in that case, H0 dl is just z. If I just take that thing, then I can see that if I just use this value and use this kind of thing, then my m actually gives you the actual luminosity or actual magnitude of the supernova will be this thing. So the low redshift supernova is actually used to calibrate the absolute magnitude of the supernova. So that I get. Then I use this supernova because I know my m, I know my small n, then I put over here, and then I get my H0 dl is comes out to be this thing at z is equal to 0.86. Now let's calculate H0 dl because I have the expression for a universe where omega m naught is 1. So this comes out to be 0.95. But if I have a universe which is 30% matter and 70% cosmological constant, this comes out to be 1.21. So one can see the rough estimate that this is much more compatible to this than this thing. Fine. So this actually gives you that okay, there is a cosmological constant. Obviously we cannot do any statistics, it's only one observation. So now we have all these observations, right, where we have plotted H0 dl versus z. These are the data, fine. The first one, the red one, which is no matter but only cosmological constant. This is no cosmological constant, only matter, and this actually is the 30% matter and 70% cosmological constant, and it seems the data actually prefers a model which is 30% matter and 70% cosmological constant. So that actually gives the Nobel Prize of these three fellows in 2011, and now we have all these data. So not only these, we have now data from all possible observational things. Total 580 data we have. So with these data, we can do cosmology and we can kind of constant different of cosmological parameters. So I stop over here. I am really out of time. But for next class, I will do the baryon acoustic oscillation and yeah, the Perlmutter, this is the oldest one. This is the first, the supernova cosmological project. This is also supernova cosmological project. And the D's itself is basically, Hamui actually first started it, but their name never came. And this is the Leaf line. So these and these two are the first data that gave the Nobel Prize. Okay, so I stop over.